Okay, 3-3 notes take 3. Conditional probability is the probability that one event has occurred given another event has already occurred. So we have a deck of 52 cards. We are pulling 2 cards. We want to know the probability that the second card is a 9 given that the first card was a queen and we didn't replace the first card. Because the first card is not a queen and is replaced, we first have to determine how many cards are left and then how many were 9s. Well, there are 4 cards still in the deck that are 9s, but only 51 cards are left because we've already pulled out that queen. We write it as P parenthesis 9/Q, where the slash means the word given. That's 4 out of 51. Okay, so we have a couple of examples. We have a box of chocolates. 5 of them are nuts, 7 of them are not. You take a chocolate out and eat it, and we want to know the probability that the second choice has nuts given the first did not. So the second choice is nuts. Probability of nuts given first choice was chocolate. We have 5 nuts still in there, but there's only 11 left. If we had done the same kind of question and they'd said a chocolate given another chocolate, then we would have chocolate given chocolate, and that would be 6 because we'd lost one of the chocolates over 11 because we'd lost one of the candies. I'll let you do the second one. Okay, independent events are events that are not affected by the probability of the first situation. So we pull a queen out of the deck, we put it back, and that means that the probability of the 4 is occurring as if the first thing never happened. So the probability of 4 given the queen's already happened is the same as the probability of just 4 if you didn't even know you pulled the queen. Dependent events is a situation where the second probability is affected by the first. So we pull out the queen, we don't put it back, that reduces our deck size, and then we pull out a 4. There are 4 4s in the deck out of 51 now in the deck. Okay, so after looking at these questions, you should be able to tell that this one is a independent and this one is independent. On both of those, they had replacing it, or they were something that was not related, like a coin and a dice. They're not related. On these two, they are dependent because they say not replacing. Okay. Multiplication rule is that the probability of A and B, when it says the word then or and, we are thinking we think multiplication. Multiplication means that you're going to take the probability of the first event times the probability of the second event. What changes is if the second event is dependent on the first. So if it is a dependent, we'll do probability of the first times the probability of the second given the first. If they are independent, it's the probability of the first times the probability of the second. And again, the words then or and are the clue that we're using the multiplication rule. So we have a problem where they have 2 cards. Without replacing the first card, they pull a queen, a king, and then they pull a queen. So a king and a queen, there's the word and, probability of the king times the probability of the queen given the king, because they are dependent because they did not replace it. So then our probability is 0.006. Mutually exclusive events are things where the 2 events cannot occur at the same time. So they have to be going on simultaneously. Therefore, A and B do not touch at all. So you can't roll a dice and get a 6 and a 2 simultaneously. So in this case, we have a randomly selected male student and a randomly selected business major. Can there be a male student who is also at the same time a business major? Yes, which means it's not mutually exclusive. And you would see that on a Venn diagram by seeing them crossing over. Can you have selecting 2 cards from a deck and selecting a 5 from the standard deck? Oh, can you select a 2 from the standard deck and select a 5 simultaneously? No, they are not going to be the same card, so they are mutually exclusive. This is not the same thing as being independent or dependent. They are totally separate concepts. They're not saying that this one is dependent on that one or vice versa. They're saying, can you do them at the same time? Okay, randomly selecting a queen and randomly selecting a heart at the same time. Yes, there is a queen of hearts, so that's not mutually exclusive. If something is not mutually exclusive, we would see the word or, and we're going to use the addition rule. The addition rule says take the probability of the first plus the probability of the second, and if they're not mutually exclusive, we have to subtract off the fold over. So if you remember the previous example, I showed you a Venn diagram where we had the probability of getting a male, probability of getting a business major, but they have a crossover here. That's the and area. You need to pull one of those off so that you're not double booking. And that's why we subtract off the and. Then, if they are mutually exclusive, we simply add them together because they are in two separate bubbles. So is 4 also an ace? No, it's not. So they are mutually exclusive, and we do the probability of picking just the 4, probability of picking just the ace, and add those together, and we get our probability of 4 or getting an ace. Okay, I filled these in. I'm going to go ahead and let you kind of look through them and do it on your own. The last thing we want to look at is permutations. Permutations are found by using the n factorial. N factorial means take that number, the sample size, and multiply it by every number behind it going back to 1. So if we have a sample of 9 cars, to figure out how many different final standings there are possible, we would take 9 factorial, which is 9 times 8 times 7 times 6 times 5 times 4, etc., back and getting 362,880 standings possible. What this does is lets us know how many different ways we can combine things, and that way we can get something in order. So one of the ways we can do that is permutations. Permutations occurs when there is everything is a unique thing. So ABC is not the same thing as BCA, and that's not the same thing as CBA. So they are completely unique new ideas every time. The way you can remember it is position matters. So if you're trying to remember what to do with permutations, or if something is a permutation, ask yourself, does it really matter if A comes before B? If Trump is elected before, or Trump is president and Pence is vice president. If the names were reversed, would that change what the situation is? If it does, then that's a permutation. Permutation formula is n factorial over n minus r factorial. N is your sample size. R is how many you're selecting out of that sample, how many pieces, smaller group you're getting. On our calculator, menu 5.2, we will pop up like this, and you just put in n comma whatever the r is. So we want a 4-digit code. We have 10 digits. We're picking 4 slots. We put in 10 factorial divided by 10 minus 4 factorial, or we can do menu 5.2 and we put 10 comma 4 and we'll get 5,040. Sometimes we have situations where you have distinguishing permutations where they're talking about the same things, but they're also talking about different types of the same things. So for instance, you have 6 lemon trees, 9 apple trees, and 5 orange trees. They're all trees, so our n is counting all the different types of trees. But if we want to know how to do distinguishing ways that they can be planted, we would have to divide that n factorial by the number of factorials for each type. So 6 factorial, 9 factorial, 5 factorial. So permutations can be remembered as being ordered combination, meaning that it really matters if it's president, vice president, secretary, who's voted on each, or ABC is not the same thing as BCA. They are completely new set ideas. Combinations is a situation where we have without order, and we don't keep the things that repeat. ABC would be the same thing as BCA or CBA, so we eliminate the things that are the same. An example is putting your books in order on a shelf. It really doesn't matter which book you put first. it matters only if you're doing it in a specific way. But this would be combinations of different ways you could rearrange them. If you are doing a combination, the formula is n factorial over n minus r factorial, which is the permutation, but then we multiply that by r factorial, which pulls out all those duplicates. So if we have a committee of 3 people and we're pulling from 20 employees, our n is 20, our r is 3. When we do n factorial over n minus 3 factorial times 3 factorial, we get 1,140 different ways you can order 3 people out of 20. You can pull 3 people out of that 20 list. Okay, I hope that worked.